This is part 2 of section 1.3. So this is how to evaluate limits that have trig functions involved. So just like on the first side that we had already completed, the first thing you're always going to try is to substitute. Okay, substitute. Now, I don't have a specific example below because it kind of fits into the same category as above, but usually when you're going to have to substitute, these are going to be problems that involve you remembering the unit circle back in trig, you know, which uses the chart of values. Okay. Now, you may or may not be able to substitute. All right. After that, if you can't use identities to simplify it, in order to get it to something you can substitute, right? If nothing like that works, then there are two special trig limits that come up a lot, okay? There are two special trig limits. And I guess it's possible that you would see, you know, just one straight up one of these without much manipulation. But more often than not, what'll happen is it won't look like one of these, but after you do a little bit of use a few identities and manipulate the equation a little bit, it'll probably turn into one of these. All right, so one of them is the limit as x approaches 0 of the sine of x over x. And here's the thing, if you look at that function, if you look at sine x over x, and you estimate the y value by looking at the graph, and remember, we're looking when x approaches 0. So this is only true for when x approaches 0. So if you look at the graph, when x equals 0, you could predict that the y value is going to be 1, even though there's actually a hole there, which is why you can't substitute. So even though there's a hole, both sides of the graph come together, so the limit is 1. And the other special limit that comes up a lot is the limit, again, as x approaches 0, has to be x approaches 0, 1 minus cosine all over x. And again, you can't substitute because this will be undefined. There's actually a hole on this graph. But if you look at the graph, you could predict that the y value, excuse me, is going to be 0. Okay, so let's see how we can apply both of those. So we've already done those top examples in the previous video. So let's go down to the bottom of page 20 here. When I first look at this, it's not exactly that first special trig limit because of that 4. But I can think of this as like 1/4 times sine x over x. And so now when I apply the limit to this part, it equals 1. And the limit of any constant is just that constant. So this comes out to be 1/4. Now, I wrote this all out nice and neat and kind of showed you the why. But really, when you're doing this on a test or quiz or something like that, you don't have to write all this out. I mean, you can kind of look at this over here and say, oh, look, here's the special trig limit that equals 1, and then 1 times 1/4. Okay? So on this one, let's kind of use a little handy-dandy shortcut. I can look at this without actually separating it. This is the special trig limit that equals 0. Now, don't worry that this is a theta and not an x, okay? Up on these special trig limits, the x just stands for the angle. We can call the angle anything we want, okay? So when you see 1 minus cosine theta, that's virtually the same as saying 1 minus cosine x. So if this part equals 0, and I multiply that by 7, this whole thing just equals 0. Okay, so those are the most basic form of how this might look. All right, so let's look at number 21. When you first look at it, first thing we try is substitute. Well, I can't, because if I put a 0 in the denominator, it's going to be undefined. Okay, so we're going to try to use some identities, and I either want to manipulate this into looking like one of the special trig limits, or I want to get it to the point where I can substitute. Either one will work for me. Okay, so the first thing that jumps out at me is this 1 minus cosine squared is the same as sine squared. So I've got sine squared over x times the sine of x. And hopefully it's pretty easy to tell that that sine x is going to cancel one of those sine x's. So what we actually have left, now it's still a limit. I mean, if we're using good notation, we haven't evaluated it, so I can't get rid of that notation. So it's the limit as x approaches 0 of sine x over x. And now I can tell this is that special trig limit, so this whole thing just equals 1. Okay, so here's a case where identities manipulated it such that I could use the special trig limit. All right, let's look at this one. Can I substitute? No, it's undefined. So let's use some identities and see what this looks like. The one obviously that pops into our head in place of tangent, we're going to have sine x over cosine x. That's all over x. And I think I'm going to think of this as a fraction over a fraction. So an easy way to simplify is to do like outer over inner. So what I actually have here is the limit as x approaches 0. The outer is sine times 1, and the inner is x times cosine. So even though I still can't substitute, I can think of this. I see a special trig limit. I see this part just equals 1. That's a special trig limit. Okay, can I substitute 0 into the cosine? Well, yeah, the cosine of 0 is 1. So since that cosine is in the denominator, this is kind of like saying 1 over 1, which obviously is still 1. So this was a combination of a special trig limit and substitution. Okay, look at this one. And at first, you might start to look for the special trig limit sine x over x, but this is not a candidate for special trig limit because notice it's not x approaches 0, it's x approaches pi. So here's a case where you can substitute, right? This is not going to be undefined if I put a pi in place of x. So what I have here is the sine of pi, and then I'm going to square that all over 2 times pi. Well, the sine of pi is 0, and 0 squared is still 0, and 0 over 2 pi is still 0. Okay? So that's the second part of section 1.3.